Thank you, Petya, and thanks to the organizers for giving me the chance to come here and talk about this work. I'm motivated by this movie from Guillaume Duclos. Notice the 500, hang on a second, let me get the button. The 500 micron scale bar, you'll see time going up here. And you see these are microtubules that are horizontal. And if we play the movie, what's happening is that Guillaume has held it and then he lets it go and you see this beautiful bend instability. So what I am interested in for the purposes of this talk is what happens before the movie started. They aligned the flow, they aligned the microtubules with flow. So we're going to look at the general question of how does an imposed shear prevent or modify this bend instability. So all this work was funded by the National Science Foundation and particularly the Brandeis MRSCC. And I'm only going to talk about one paper today, and most of that work was done by Juan Luo, a former fluids and thermal sciences graduate student in our School of Engineering at Brown. And then there's also some work in progress, which was mostly done by Jasper Chen, who's a former undergraduate who just graduated, and we're working with Aparna, and Bob Pelkovitz, and the more recent stuff is also with Alex Morozov. So the general picture is that we're going to look at Couette flow, and you know, it's the afternoon, I'm a little sleepy, so to keep myself awake, sometimes I'll have the bottom plate moving and sometimes the top plate moving, so I don't think it'll be too confusing. But this question has been studied by many people in this room. Particularly, we've learned a lot from Sriram's papers and Christina's papers. We're going to look at the problem from the point of view of hydrodynamic stability or hydrodynamic instability. And by an active gel, what I mean, it's a liquid crystal that is in its isotropic state, and then we add activity. That's going to be the model that we use. And we've seen a lot of these equations before in this week so far, so this is really just to set the notation. We're going to be working in 2 dimensions, so we'll be using the order parameter tensor Q, whose eigenvector is the director, the eigenvalue is the scalar order parameter. Our Landau free energy is going to look like the blue curve, so this parameter A is going to be positive, favoring the disordered state. And one of the elements when we're going to be trying to understand physically what's going on is the so-called molecular field, where you just take the derivative of this free energy. We're going to neglect a lot of terms. We're going to neglect this quartic term because we're mostly considering, even though the order may get large, we're mostly considering small order, going away from the isotropic state. So we'll neglect that. So the derivative of this free energy is just the molecular field. That's the entropic force which is pushing the system towards being disordered. So here is the minimal hydrodynamic model that we're going to use. Again, we've seen this modified Stokes equation before. There are other terms that are not written here, the Ericsson stresses, the terms that have to do with backflow from stresses in the liquid crystal. I'm going to neglect all that. You can put that in. We don't think it will it'll certainly quantitatively change things. We've got the equation for the order parameter Q. So let's just go through some of these things here. Nu here has the dimensions of a viscosity. And if you just focus on the first term here, suppose there's no velocity. This would just be the time derivative of Q. So if there's no velocity, the vorticity tensor would be 0. This is the strain rate. Let's suppose that Q, let's just not worry about this term for the moment. You know, if you just align the liquid crystals at some moment and let them go, they'll relax with some time scale, which is given by the ratio of nu over A. So that's going to be the characteristic time we're going to use, you know, in all the plots that we're going to show. And then more generally, I said nu has you could think of it kind of like a rotational viscosity, right? Q's got the director in it. So if you take, you know, if the director is rotating relative to the background flow, there should be some, even if it's disordered, there should be some kind of rotational viscosity resisting that. So you want to look at not just the rate of change of n or the rate of change of q, you want to account for the rotation of the background flow. And that's exactly what this co-rotational derivative does, where again omega is this vorticity tensor. And then, you've got the usual coupling to the strain. E, the strain rate here is not sensitive to the rotation, but if you have an extensional strain, the rods will tend to align along the extension. Okay, so this is sort of I already mentioned this relaxation time, the liquid crystal relaxation time. Of course, there's the active time scale that you can make out of the viscosity and this activity coefficient. Roughly speaking, we expect to see that instability when these two time scales are comparable. There's characteristic length scales, which we think about, but I'm not going to emphasize them very much. Okay, so let me just review the kind of classic picture of this bend instability that I learned about actually when I was preparing for these lectures 20 years ago. Well, not quite that long, from Sriram's paper. Let's go forward. So, if you take rods and you put them in a shear flow, and it's a weak shear, so think of this like an infinitesimal shear, like some kind of perturbation. The rods, you just look at those equations or think about it physically, the rods will align so that the eigenvectors, the directors, will be along the principal directions of the shear, right? So it's going to be 40, as soon as there's a little bit of shear, the rods will be at 45 degrees. There'll be a very small amount of scalar order, which is proportional to the strain rate. So that I preceded my point. This is the paper I wanted to mention. It was from 2002. Again, this is really just to set the notation. When A is positive, we're talking about extensile particles, like those microtubules. And these particles exert forces on the fluid. If it's contractile, it goes the other way. So if you put these two things together, you can see, now imagine that we do have plates and we're sliding the plates, maybe with your hands, as I've shown over on the left here. That will make these rods come out in order at 45 degrees to the flow, and they're pushing, and there's a component of force in the same direction that your hands are moving. It's helping you move the plates, so effectively the viscosity has been reduced, and you just, all those words I just said are represented in the equations. That's exactly what you find. The viscosity gets reduced in the case where the particle is extensile, where A is positive. The opposite effect when it's contractile. So let's suppose those plates are very far apart. So I'm just going to imagine a infinite domain, and suppose we have a little perturbation of flow. So the base state here is that there's no order and no flow. So I'm not applying an external shear yet. And you have this little perturbation of the flow. And what will happen? Well, in the regions where there's a high amount of shear, the rods will align, like in this orange region, or the other way in the blue region where there's not much shear here, they'll be more disordered. But if the activity is high enough, there'll be no effective viscosity resisting this flow, and it will continue. It won't be damped. And that's essentially what you find. And in fact, this argument gives you the correct, even for the numerical factors, the critical activity. And that's the basic background. So now what we are interested in is what happens when we have some finite shear rate. So the base state will be the base state will be that there is some alignment, because when you have an external shear, it will align the rods. So again, if it's weak shear, it'll mostly be at 45 degrees. If it's strong shear, and weak and strong is compared to this liquid crystal relaxation rate, if it's strong shear, the rods will be aligned along the flow lines. And you can work out the details. And what we want to do is solve this problem, the linear stability problem. And for the first part, our first attempt is we're going to look at a one-dimensional perturbation where the order parameter tensor Q is only going to vary in the y direction. And now we actually are going to imagine that there are plates here, but we don't have to worry too much about those details. And likewise, the variation in the velocity in the perturbation is going to be varying only in the y direction. No variation along the x direction, because if we make that assumption, then this term, you know, the advective term v dot grad q will just vanish. And that's the term that makes it a little more difficult to solve. Certainly you can't solve it analytically if you have that term. So the effect of the shear is to increase the critical activity. And again, we can understand that from these pictures. What is the effect of the shear? Well, as you increase the shear at some finite amount, the rods are going to turn over more and more and align more and more. So when the rods are completely aligned with the flow lines, you wouldn't expect any active contribution to the wall stress. Of course, they would be more ordered there, but you know, you would get more of an effect when the rods are not completely aligned. So you can work that out, and the base effect is that you're going to get less and less of this reduction of the viscosity when you have more and more strain rate, more and more gamma dot. That is to say, you're going to need a higher activity to get the system to go unstable. This is a rough argument. It's not going to give us the correct numerical factors like the kind of infinitesimal shear rate argument gave us, but it gives us the right dependence for how the activity, the critical activity, depends on the strain rate. So we can be more quantitative and work out the details. We can work out the growth rate, sigma. So in these figures, I've gone back to the case where the plates are very far apart, and there's no Q dependence, no wave vector dependence. In the case where there's zero external shear, okay, so what's on the x-axis? The x-axis is the dimensionless activity, extensile to the right, contractile to the left. This is the classic picture. There's actually two modes. One in which the liquid crystalline degrees of freedom simply, if you have some perturbation where you have some local order, they just relax exponentially with the liquid crystal relaxation time. That's this mode. And then there's the growth. And if the activity is high enough, so 1 in these units, you get some growth. Now, if you turn on the shear, something sort of interesting happens. These modes mix, and where they mix, you get the red is the imaginary part of the growth rate. You get some oscillation. So if it's a weak shear, not much happens. The critical activity has increased, and the place where you have these oscillations is where the system is still stable. The modes are exponentially decayed. But as you keep increasing the shear rate, this bubble of imaginary growth rates grows and eventually overtakes the point where where the system goes unstable. So even the growing modes become oscillatory. And if you look down here, in this case, this is the contractile. These branches correspond to the contractile case. They're still stable. But one thing that surprised us, note the difference in the activities here. The scale on the graph at the right is much larger activities than on the left. You see that even the contractile system is unstable to something. So we can summarize all this. Maybe it's a little bit easier to take in here. A kind of stability diagram where, again, on the x-axis we've got the strain rate. On the y-axis, maybe if we just focus on the case of zero strain rate, this is the stuff that's been studied very, very much. The contractile liquid crystal is always stable as far down as you go, and that's our critical value of and you see that this, as you increase the strain rate, this goes up, right? So that's this quadratic increase of the critical activity with the strain rate squared. The blue region is stable. The pink region is those oscillatory modes, or where the growth rate is complex. And, you always get a little bit of oscillation. We think this is somehow the remnants of the Jeffreys orbits. When you shear rods, they rotate. That's something interesting to think about. And yeah, right. Once it's high enough, even the growing modes can be oscillatory. Once, that is to say, the shear rate is high enough. And there's a kind of surprising region, which we didn't expect, that for large strain rates, when it's contractile, it's unstable. That is to say that the shear is not always stabilizing. It can also be unstable. Now, I gave you a physical picture for...
Tom?
Yes?
Sorry. For which wave number is this? Is this at some finite wave number or at zero?
This picture is actually for the case where the plates are very far apart. When the plates are, I'll show it's
in the infinite wave number limit.
This is infinite. It's actually, in that case, it's independent of the wave number. When the plates are closer together, actually it's hard to tell. You'll see on the next one, when the plates are closer together, that'll move this up a little bit, right? Because confinement makes things more stable. So we account for that. I'm not going to show you plots of that, but when we do it numerically, just hang on. We account for these wave numbers.
Yeah, just because Vincenzo's no longer here, I'll take his role and point out that where the oscillatory and unstable modes meet is an exceptional point. So that might be interesting to some people.
Yes. Okay. Thank you. Thank you. Okay. So the next thing we did was use numerics to solve the full nonlinear equations, and it's appropriate, I guess, that I'm giving the talk here because we use Phoenix, and we got the idea to use it in the pandemic membrane KITP, where Andrei Kazmiral's tutorial on Phoenix inspired us. So now we've got a finite system, more or less of the dimensions that you see here, and the boundary, we impose periodic boundary conditions at the inlet and the outlet, no slip boundary conditions on the velocity. You know, you could put anchoring conditions on the walls, but we don't. We just use natural or so-called, it's like torque-free boundary conditions, just because then it's easier to compare with our analytical calculations that I showed on the previous slide. So here are the results of the numerical solution of the nonlinear equations only for the positive activities. The blue is the same blue that you saw in the analytical calculation. So this boundary is the boundary from linear stability analysis. The x's are Couette flow, simple shear. The circles are again, all this stuff is known for the case of zero strain rate. This is just unidirectional flow that you get in the channel. And I'm not going to talk anything about what happens at the high values. You get these dancing flows. The triangles are a kind of oscillatory flow, which is not this is unsteady. And what you notice is that let's see. And this dashed line is the boundary. You know, below this you have oscillation. So in the linear modes. So you see good agreement between the numerics and the linear stability until you get out to some moderate strain rate. And it's also right around where we start to see these oscillatory modes. So we'd like to understand why, what's wrong with the linear stability calculation out here where it suggests these, the Couette flow should be stable and it's not. So let's just briefly review. Again, this is the only difference here. This is the unidirectional flow state that the system is unstable to at small strain rate. The only difference is now we're moving the bottom plate. So the color red is higher velocity, blue is lower velocity. The top plate is not moving. So you can just look at this and see that you're going to get this kind of splay, and you can think about minus the activity times the divergence of Q, and that active force, it's going to have a perpendicular component at various points as you go across, but that's just going to balance with the transverse pressure gradient. It's going to push the fluid to the right. The flow can go to the left or to the right, but because you're moving, that is to say the spontaneous activity-driven flow can go to the left or to the right, but because you're moving the bottom plate, the net flow will look a little bit different. So that's the red circles. These blue triangles are the oscillatory flow. And as I said, it's unsteady. And, well, we're just showing the directors below and the vector field for the velocity above. And it's certainly not one-dimensional. So this maybe now you can see why our simple one-dimensional perturbation didn't work, because the state that the simple shear is unstable to is not a one-dimensional unidirectional flow state at high enough strain rate. right? So there, whoops. So let's now turn to a more, you know, so we therefore should look at a two-dimensional perturbation where the order parameter tensor Q and the vector field should depend on not just y, but also on x. And then this term is now going to depend on y, and the coefficients are not all constant. But this is something that people have studied for many years in fluid mechanics using spectral methods, for example, which is what we do. So this is the work that's still ongoing. And again, I'm only showing the extensile case here. And the dashed dotted line is the boundary from the linear stability that we saw earlier. The solid line is the result of this numerical spectral method. If you look carefully, I'll just tell you, these lines may look like they're crossing, the dashed dotted line and the solid line, but they're not crossing, which is good. They shouldn't cross. We don't get exact agreement. You know, again, this is work which is ongoing, that we're looking at two slightly different things here. In the numerical calculation, the size of the system is finite, whereas in our spectral calculation, we have wavelengths which are longer than that, you know, finite length. Because in principle, we're looking at an infinite channel, and of course, we cut off the wavelengths at a certain point. But even so, it gives us a much better accounting of what happens here at higher strain rate, right? So all these states are, which the linear stability calculation said were unstable, of course, which the linear stability calculation said were stable with one-dimensional perturbation, they are unstable because of the two-dimensionality of the perturbation. Okay, so let me turn in the remaining minutes to the contractile case. I don't have that much to say about it because we don't have a simple physical picture for why the contractile flow is unstable, or the contractile case is unstable due to the imposed strain rate. One thing I will tell you is that we only ever see these unidirectional flows. That's consistent with the fact that, at least on this diagram here, as far up as, well, we've gone much farther in the strain rate. The phase boundary is always below this curve. Again, the boundary between the oscillating and the non-oscillating growth rates. You know, we can just look at the flows. Let's just focus on the top, the kind of positive spontaneous flow. Again, the bottom plate is moving. It almost looks plug-like, although there is a little bit of strain or shear in the bottom here. And then as you go up to the top, it really drops off very dramatically. So we see a kind of boundary layer in the flow. And if you just look at okay, there's bend here and there's splay, but if you look at the divergence of Q, it's really the splay part, n dot divergence of n, which is giving the active force which is driving the system. And just because of the way that the directors are ordered, it gives the force to the right. So that's not an explanation, it's a little bit hand-wavy, but that is our picture for how this is consistent, right? And here I'll just flash a picture of the boundary layer. There's some simple scaling things that we don't quite understand, where if you take the flow velocity and subtract off the strain rate and just look at the activity-induced flow, and this is a very high strain rate, or it's very high activities that we see this boundary layer. You know, of course, because it's unidirectional, it's much easier to do the calculations at high activities. So this is a good group to show this graph to, because it seems like this would be very simple to understand, but we don't have the answer. Okay, so I took out one or two slides just before, but I think that's okay if I end a little bit early. The conclusion is very simple, just that when you look at this problem of the bend instability with shear, that the shear stabilizes extensile particles, but it destabilizes if the shear is sufficiently large, the contractile particles. This 1D stability analysis fails at moderate shear rate, and it's not hard to see why, because the state that it's unstable to is two-dimensional. We are working on looking at this in 3 dimensions. We know from experiments, from Kunta-Wu and Seth, and we know from Aparna's work that 3 dimensions is very different than 2 dimensions. There's things that are very different from what happens in kind of classical fluid mechanics where you can get away going from 2D to 3D. We know that does not happen here. The flow in the experiment that I showed you at the beginning was not a Couette flow, it was a Poiseuille flow. So, and I know others have worked on this case more recently. And in any comparison with experiments, maybe since there's time, so one of the things we've looked at, what might be a little simpler, is to look at the case of a, simpler experimentally, the case of a rotating disk. This is something Kunta-Wu is working on. In any case, when we look at experiments, there's this, we've seen it many times. We saw it in Peter's talk that, and when you turn off the activity experimentally in the system, you get a gel. When you turn off the activity in our theory, you get a liquid crystal. So, we have to grapple with that, and that's something for a future direction. So I will stop there.
Thank you. Questions? So let's.
So, I mean, this is just a hypothesis, but it looks a little bit like shear banding, what you observe in the contractile case. Have you looked into the literature? Maybe there's some hint on how that regime might work.
I agree with you.
Sort of a bistable situation somehow, and then it just interpolates with an interface with a domain wall between these two.
Thank you. I think that's a very good suggestion. We've been reading Suzanne Fielding's work on this, and so we know about this, but we haven't yet gotten to the bottom of it.
Yeah, Tom, you include, if you look at the passive part of the dynamics, you include the term proportional to the rate of deformation in the Q equation.
Yes.
But its sort of Poisson bracket partner in the momentum equation is absent. Is that important?
I think ultimately is important. I think this is one of these, we are basically going on the work of others where they neglected it and it didn't seem to make that big of a difference. We didn't actually include it to check. We worry about this. Again, this is the kind of thing that my thought is if we were going to look at experiments, we would double check that for sure. But I don't, so my honest answer is I don't know, kind of relying on what other people have done. But yes, it's something that we worry about.
So maybe I missed this, but in the case of the annulus and also the other case where you showed the flow kind of translating, what is setting the wavelength?
Yes, yes, we've worried about that. The first thing we worried about was whether or not this was just an artifact of our periodic boundary conditions and it just somehow was just drifting. So that's actually why we did the annulus, because at least in the annulus we had a single domain with no periodic boundary conditions. The wavelength seems to roughly be set by the gap. We can get different number, like here, you have to get an integer number to fit in, but not always. It doesn't always have to be this way. We didn't systematically study this. We changed the length to make it much longer. And depending, it has to do with the initial conditions. There's kind of a broad range of initial conditions where we more or less got what you saw. But sometimes we could get an extra wavelength or one fewer wavelength. Same thing here, or maybe it wouldn't be quite perfect. So we haven't really studied that. That's basically all I can say. I guess the other thing I can say is that, you might ask, how does that affect these boundaries in this diagram of flow states? And there's a couple points where, maybe this triangle moves down 1 point or something like this. It didn't seem to affect these boundaries very much. Here, things were much more fuzzy. Up there, it seemed to have more of an effect.
Thank you.
Okay, going back to Sriram's question, have you looked at the role of this flow alignment parameter, what you call mu, in your equations? Because when you include the terms that Sriram was talking about to linear order, there is actually kind of a mapping between, let's see, flow aligning extensile and flow tumbling contractile. So So I was wondering whether you looked at...
I think that is more important in the active pneumatic case. So we haven't extensively studied it here, but here they're always aligning because you have this isotropy, you know, the driving force towards isotropy was tending to erase the
So I was just wondering whether in the contractile case you have looked at the values of mu.
Okay, no, we haven't
flow
done that.
tumbling.
Yeah, no, it's a good suggestion.
Okay.
Yeah, thank you.
Could you say a bit more about the mechanism of the oscillations? You hinted at the Jeffreys orbit.
Oh.
I don't know if you understand it beyond that.
Yeah, well, let's see. Why did I say that? This is why I said that. So let's just think of a passive liquid crystal. No activity, but it's in the isotropic state. So, you know, if there's a small amount of shear, in the steady state, it'll be close to pi over 4, right? That's the alignment relative to the... So that's what we've done here. We've solved the startup problem. And then as you increase the strain rate, the imposed shear, you know, it's getting closer and closer to the origin. And then if somewhere between 1 and 5, you start to see these oscillations. And it doesn't just go directly to the steady state. You see these oscillations. So this doesn't have anything to do with activity. It's, I think it is like what Christina was saying, that, you know, we see this experimentally depending on the flow aligning parameter in pneumatic liquid crystals in the startup problem, where they can oscillate before they even in flow aligning liquid crystals. But we don't have that here. This is, you know, this is just coming from the balance of that rotational, you know, the co-rotational derivative with, that's balancing with the entropic force, which is tending to make it isotropic. So that's what sets this, final position. And really you know, you've got this extra term, the extensional flow, which is tending to make the rods align at 45 degrees. So it's really just the, I mean, if you throw away the driving force to isotropy, the rods would just rotate, right? So that's why I think it has to do with the Jeffreys orbits. And when you add that damping term, the thing that's driving it towards isotropy, then you get this oscillation.
Thanks.
Just so very briefly, you mentioned the boundary conditions you used in your numerical solvers, and you had free boundary conditions on your director. But given the sort of director profile you have, even for this unidirectional flow state, if you had these strongly anchored boundary conditions, that would go away, right?
Well, I think typically what people see in these active systems is that the boundary conditions, you know, when things are being driven hard, don't seem to matter very much. We haven't checked that, so it's a valid question. It's something we should certainly consider. So, you know, I guess I can say, well, we haven't looked at that, but that's why we didn't do that.
If I can sort of self-pitch, we kind of did, and
okay.
You sort of lose these translationally invariant states if you do have strong anchoring, and even the first sort of excited states you get are not invariant in this direction, and you get these flow vortices.
You only get the oscillations.
Yeah, or modulations of that.
Okay.
We did not at all consider shear rates, like external shears, but just boundary conditions, and with the strong anchoring, the simplest states are.
Oh yeah, I'd love to see more about it.
Go ahead.
Yeah, I just wanted to briefly come back to these pattern states. So you showed that the pattern itself travels. Is the traveling speed somehow related to the shear rate, or does it somehow travel relative? Could it travel backwards? What sets that velocity essentially?
That's also something that seems that we should understand that we don't. Well, I can tell you what sets the velocity. At low activities, the velocity is close to the average velocity of the fluid. So it's as if it's moving with...
So co-advected.
Yeah.
Okay.
And then when the activity increases, there's actually a regime where it's exactly equal. Not just at a point, but over. So that's what I think it's setting it. Again, there should be some simple explanation for why that is true, and we don't have it.
Well, it could come out in the linear stability analysis already.
Yeah.
Because it's presumably a finite wavelength instability, and then you have an imaginary part. Basically, the ratio of the imaginary part to the wave number gives you a velocity, and that could just be the velocity.
Agreed. We just haven't done this one. It's more complicated with all of the variation in X and Y. Agreed.
Great. I think we are ready for some nourishment and for the discussions on the coffee break. So thank you, Tom.